All right, let's get started. So, like I was saying earlier, we will finish chapter 2 today, and I cannot wait. So what you'll find is that we're going to find derivatives, which I've already kind of mentioned. We're going to be doing for the rest of the course is working on derivatives, because that is Calc 1. And so now we have the tools to kind of establish what a derivative is today. And then don't worry, finding derivatives will not always be this cumbersome. We're going to have shortcuts for finding derivatives, and that's what the rest of the course is about. So we will find derivatives today, but it's a little bit longer because we're using the limit definition of the derivative. But then just
we're starting with basics.
Say that again.
We're starting with the basics, essentially.
Yeah. So it's like, hey, here's what's going on in the background. And then later, I'll say things like, aren't you glad we're not using the limit definition of this thing? So, yeah. So we'll have shortcuts, just kind of hang tight. That's the fun part of the course. We need to get through this first. So just as kind of a quick review, we started talking about derivatives, and we kind of have two definitions of derivatives. The first one is kind of my go-to definition of the derivative, and that's that it's the slope of the tangent line at some point. So it's the slope of the tangent line I guess it's understood on some function, right? So the slope of the tangent line at some point x equals a. Okay. The other option of thinking of this thing is, of course, the slope of the tangent line. The tangent line is just the rate of change at that particular point x equals a. So what we can think about is that it's the instantaneous rate of change at x equals a. So derivatives, there's kind of two ways we can think about it, but it's the instantaneous rate of change at x equals a. Okay. Versus, so here I'll just kind of throw in versus the average rate of change, which would be the slope of the secant line, right? The slope of the secant line is the line that connects 2 points on the curve, right? Whereas the tangent line only touches the curve at one spot, x equals a. Versus the average rate of change, which is the slope of the secant line. Right, so just kind of keep those two separate in your mind. And for a lot of section 2.1, 2.2, what you were finding were the slope of the secant lines, right? Moving that point closer and closer to the point of interest, and then finding the slope of that line as you move closer and closer to, right? And then using that to estimate what the instantaneous rate of change or what the slope of the tangent line is, right? And so we kind of move those points closer and closer to, okay? So same idea, but what we said last day was, okay, so the slope of the tangent line at some point x equals a, well, what we said was, okay, well then the slope of the tangent line I can find using a limit, the limit as h goes to 0 of, and I want to use the right one here, of f of a plus h minus f of a over h. And this is going to be the slope of the tangent line at x equals a. Okay. So this is the slope of the tangent line at x equals a. Same idea, right? We can use the same idea for the velocity. And we did an example on parking lot that, but just remember that if you have a distance function and you have to find the velocity, right? That is the slope of the tangent line of the distance function. Okay, so recall that the velocity at x equals a is the slope of the tangent line of the distance function at a. So we said the velocity at some point a is the limit as h goes to 0, but this is the exact same function, right? F of a plus h minus f of a over h. So these two, right? Just kind of convince yourself, okay, you got the limit as h goes to 0 of f of a plus h minus f of a over h. The hard part is remembering that, okay, well, the velocity is the instantaneous rate of change as we move along this curve. Okay. So what we want to do today, that's kind of the end of the review, so close to the end of the page, I may as well start here, is that we want to introduce the derivative, which I have talked about, but we haven't really, said, okay, we're going to calculate a derivative now, but here we go. So this is from the 2.7 notes. Down here, you've got definition 4. So the derivative of the function. So here we're actually calling it a derivative. So let's nab this portion here and bring it in. Okay. So there's some, and I can't remember if I introduced this notation. I don't think I did last day, the prime notation of prime of a. Okay, so let's talk about this. How do we read this? Because what you can kind of convince yourself is that, well, okay, the limit as h goes to 0 of f of a plus h minus f of a over h sounds familiar, right? From up here, right? And also up here, right? So these are all the same limits. But now we're calling it a third by a third name, okay? And that is f prime of a. So here, I want you to read this as f prime of a. Okay. So that prime indicates the derivative. So that little asterisk, we use prime to indicate the derivative of f at a. So, of course, there's only a derivative if the limit exists. So there are cases, which we'll talk about later, where the derivative doesn't exist. Okay? But in general, right, so that would be cases where the slope of the tangent line doesn't exist or there is no tangent line, right? Then you would have derivatives that don't exist. But like I said, we'll talk about some common situations where the derivative does not exist. So we use this little prime to indicate that, okay, I'm taking the derivative of the function f and evaluating it at a. Okay? So, but we already talked about the definition of the derivative, right? The derivative is the slope of the tangent line, which you could also think about as the instantaneous rate of change, right? And so we already have those definitions. So it makes sense that, well, if they all mean the same thing, the derivative is the slope of the tangent line, is the instantaneous rate of change, well, then they should all have the same function, right? They should all have the same limit definition. So it just depends on the problem, what you're trying to solve for, right? But I want you to notice that f prime of a is the same as m, which is the same as the velocity at a, depending on the situation. Yeah? Usually this connection, the derivative being the slope of the tangent line, is the one that we use the most. Okay. So let's do an example where we use this limit definition to find the derivative. So example 4. So now I want to find the derivative of this function f of x equals x squared minus 8x plus 9 at the number a. So at any number a, it doesn't matter. And what's nice, if we have a placeholder like we found in that last example where we finished last day, if we have the general function, then we can just plug in whatever a we want and solve for, it was the velocity in that case. But so now let's find the derivative of this function. So now I have this function called f, and I want to evaluate it at some number a. So what that means is, well, then I want to find f prime of a. So let's copy out the definition here. So f prime of a is, and I'm just copying out the definition, the limit as h goes to 0 of f of a plus h minus f of a divided by h. So now I want to write f of a plus h, which is a plus h squared minus 8 times a plus h plus 9, and then minus f of a, which is a squared minus 8a plus 9. Right, so just keep those kind of separate. But we've worked with enough of these difference quotients that we can kind of do them on one line. But if you want to split them up, that's totally fine, and then rearrange them. That's fine. The limit as h goes to 0 of, and I'm going to use big square brackets, a plus h squared minus 8 times a plus h plus 9 minus, keep that negative outside, f of a is a squared minus 8a plus 9 divided by h. Keeping in mind that if things are falling out the way they should be, eventually we'll be able to kind of cancel this h in the denominator, which is really making a mess with our limit, right? So until we're able to kind of move this h or kind of rearrange it, we'll need to keep manipulating this thing. So let's see here. The limit as h goes to 0 of a plus h squared, I always write it out, and I know I tend to show more work than you have to, right? But I like to be able to visualize a plus h times a plus h, because I don't know, for some reason I just have a hard time expanding that. And then minus 8a, kind of different levels of expansion here. I'm going to expand this -8 inside here. And then next one, I'm going to expand this negative inside f of a. So I get -8a minus 8h plus 9 minus a squared plus 8a minus 9. Being careful to expand that negative across the board here. For 8. Limit as h goes to 0, just to save us a line of work here. How about I just do a squared plus 2ah plus h squared. Right, I've expanded out that a plus h times a plus h. Minus 8a. In fact, let's take this thing home. I'm going to ditch these square brackets because I don't actually need them anymore. There's no negative outside or no multiplier, so I don't need it anymore. Minus 8h plus 9 minus a squared plus 8a minus 9 over h. So many things are going to cancel out, and it's awesome. I don't know, for some reason it just feels so good. A squared minus a squared, negative 8a plus 8a plus 9 minus 9. So typically what will happen is this these last few terms will always cancel out. There's no h in it, so they always cancel out. But hate to say always. I haven't looked at all the different scenarios. So, but now what I'm left with here is 2ah plus h squared minus 8h. I've got a common multiple of h, which I can extract, right, factor out to the outside. So I have the limit as h goes to 0 of h times 2a, oops, clean that up a bit, 2a plus h minus 8 over h. Finally, can ditch those. If I let, so now what I have is the limit as h goes to 0 of 2a plus h minus 8. So if I take that limit, h is going to go away to 0. And so I'm left with, this becomes 2a minus 8. That's my limit. Let's see where I'm at here. Okay. So, right, what we've found is that the slope of the tangent line, right, because remember the derivative of f at a is going to be the slope of the tangent line at some point a. So now, regardless of what value of a I put in here, I'm able to calculate the slope of the tangent line at any value of a. And that's going to be really useful, right? So here, this, let's just grab the definition from here. But then I'm also going to write it out in kind of plain words here. So the tangent line of this function at some point a, and of course the y value being f of a, is the line through that point, right? Because it has to go through that point, but only through that point in order to be the tangent line. And then the slope of the tangent line is f prime of a, right? Or in other words, what this is really trying to say is the slope of the tangent line at A is f prime at A. So what we found, right, is that, okay, we have this function, this original function, x squared minus 8x plus 9, right? And so now I'm able to say that the slope of the tangent line at any value A is going to be 2A minus 8. That is good. So what we've found in example 4 is that the slope of the tangent line at A, and then of course the y value of the function is f of A. So it can get confusing to figure out, okay, when am I using my original function and when am I using the derivative, right? But just remind yourself that the derivative is the slope of the tangent line. So then at A, f of A is the xy point at A. So what we found is that the slope of the tangent line at A, f of A, is 2A minus 8 at x equals A on f of x equals x squared, and what was it? Minus 8x plus 9. So laggy. Looks like an underscore, not a minus. There.
Would that not be f prime A, or is it just FA?
This one here.
Yeah.
So this is the point of the like where we're finding the slope of the tangent line, but then this is the derivative. So f prime of A, which is 2A minus 8, 2A minus 8. So we've got this function, right, which is probably a quadratic. It is a quadratic. So it's going to look something like kind of generic like this. So then if I pick a point A here, then this point is at A f of A. Oops, right, xy. And then the slope of the tangent line, which is going to be the line that goes only through that one point, A f of A, slope is f prime of A. But what we've found is we're letting
sense.
Pardon?
That makes more sense. Yeah.
Yeah, so I'll admit it can be really tricky to keep track of, okay, my f of x versus f prime of x, but it's just going to take practice, right? And it's okay to be confused. I think I was confused about it for the whole term that I took this course. So I mean, it's not. I found it very confusing to keep track of the function versus the derivative, but just kind of got to stay on top of it. Okay, so good. I think we're going to use that same function and derivative, yeah, in example 5. So let's just go ahead in example 5, because now we're going to use the fact that, okay, the derivative is the slope of the tangent line. So if I have the slope of the tangent line, I can find the equation of the tangent line if I have a point on there, right? So given a point on the tangent line, we are able to find the equation of the tangent line. Using y minus y naught is m times x minus x naught. Right, so given some point x naught, y naught, so here, where m is really the derivative of this function, right? So let's do this example 5. So find an equation of the tangent line to this parabola. Notice that this is the same function. Why is it x naught and, oh, did we use x1, y1? I can't remember. I think in pre-calc they use one notation, even though it's the same authors. And then in calculus they switch to another notation. This is the same as, it doesn't matter which one to use. Y minus y1 is m times x minus x1. It doesn't matter.
It's literally just denoting this x is not the same as the other x. So
yeah, exactly. So it's just a placeholder, but x naught, y naught would be the point that you have, or not y, x1, y1.
You could theoretically you slap anything as the little denote.
Yeah, like if
add
you
little
wanted,
heart symbols if you particularly wanted to.
if you want to do A and B, that's fine too. Although I don't think I've ever seen that. These are the only two that I've really seen in action. But yeah, I know it gets confusing. And David came in. I had office hours before this, and or I was just meeting with someone, and we were going through this exact same problem. And now I'm worried that I used a different notation with her than I did in class with them, because I thought you guys were using the knots and not the ones. Anyways, doesn't matter. They're the same. Yeah, doesn't matter. But yeah, very confusing if you're used to seeing it one way and only one way. All right, good. Got it all. Okay, cool. Yeah, so if you're used to, just stick to what you're used to and then just kind of program your brain to use them interchangeably. I know that's not very fun, but yeah, totally. No, it's good to ask. Sometimes it's not what you think it is. So, good. All right. Good. That's like for y equals mx plus b, because I do statistics mostly, typically. There's like 4 different ways, or 4 different common ways to write y equals mx plus b, y equals ax plus b, b naught plus b1x. Anyways, they all mean the same thing. So confusing. All right. Oh yeah, so here, notice that this is the same parabola as from example 4. So here, same as example 4. Okay. So what I'll say is, since f of x, and what I'll say, because here they've got y, but just remind yourself that y and f of x, you can read those interchangeably, right? f of x is just highlighting that the curve f, right, which is just the name of the curve, takes some input x, which makes sense because here we've got just a bunch of x's, right? So it varies depending on x, but really, if we're just talking about x's, then the other variable would be y. So f of x equals y, which is x squared minus 8x plus 9. We know from example 4 that we found f prime of a, which is the derivative at some value of a, was 2a minus 8. Okay. Good. Okay. So we want to use this, so the slope at some value of a is 2a minus 8. In this case, the point that I'm interested in is at 3, negative 6. So at x equals 3, well, I can let a be 3. So we want the equation of the tangent line, the equation of the tangent line at 3, negative 6. And if you plug in, so just kind of to check it out here, if you plug in x equals 3, the y value should become negative 6. Otherwise, it's not a point on this line, right? So 3 squared is 9 plus 9 is 18 minus 8 times 3, which is, well, it should be negative 6. Why can't I do it? 18, 8 times 3 is?
24.
Thank you. 18 minus 24 feels like minus 6. Sold. Moving on.
Yes. Yes, that works.
Great. Otherwise, it wouldn't be a point on this line, and thus it wouldn't be a tangent line. So, okay. Great. So what we've got here is, okay, well, at any value of a, we've got a slope of 2a minus 8. So now we let x equals a equals 3. So then at a equals 3, f prime of a, I'll just write out the general formula here, is 2a minus 8. So then f prime of 3 is 2 times 3 minus 8. Phew. Negative 2. So this is the slope of the tangent line. So I'm going to have a negative slope at x equals 3. Okay. Okay. I'll highlight that. The slope of the tangent line at x equals 3 is negative 2. So, and we can draw this in Desmos just to make sure that that makes sense. The only reason I'm kind of hesitating and I want to draw it out just to check it is because, well, like I said before, this just feels like a parabola to me, right? It's just going to have this kind of basic quadratic shape. And so depending on the shifts and stuff, but as it sits at the default origin, I wouldn't have a negative slope at 3. So that's why I just want to check to see that a slope of -2 actually makes sense. So what I'm going to do is I'm just going to draw x squared minus 8x plus 9. Oh, that's the wrong window. On here. So I get x squared, where's the original function? Minus 8x plus 9. Okay, so, and then I'm interested in at x equals 3. Okay, so now this is the point that I'm interested in, and that's the point that I'm finding the slope of the tangent line of, or in fact, the equation of the tangent line at. Okay, so it does make sense to have a negative slope, right? So you can kind of talk yourself into what you're doing by checking the original function. Great. Phew. Yeah. But it's always good to have those kind of internal checks of, okay, so I found a negative slope. Does that make sense? Yes or no? Right? In this case, it seems to make sense. So we're moving on. So then, given that m is -2 and the point, sorry, not -3, 3, -6. We find the equation of the tangent line and we'll use that point slope form. Do I stick to ones or do I go for knots? You know what? I'm going to go with knots because I feel that's what they might use in Calc 2. So I like to show off with these knots. So y minus y naught is m times x minus x naught.
It was what they were using last semester in physics, so.
Using the knots?
Yeah.
Yeah, I feel like we like to use the knots, but we also like to confuse you guys.
Well, that is kind of the objective of university. Strategic confusion until comprehension is reached.
Exactly. I just feel like at the end of my undergrad, I felt like, okay, the whole point of this exercise was just to teach me how little I know. Right. And so it's not until you go into and it's like, wow, there's really so much I don't know. It's crazy. Yeah, so that's school for you, just to teach you how little you know. All right, so our points here, y minus -6, let me clean that up, is -2 times x minus 3. I get y plus 6 is -2x plus 6. Y equals -2x plus 6 minus 6, just to emphasize, y equals -2x. I'm going to draw, since I have it in Desmos, the original function, and what I'm trying to draw, I'm just going to draw this on the same graph. I'm going to get rid of x equals 3. That was just to make sure. And y, well, let's just try -2x. Looks pretty good. It looks like, I mean, it's not going to do a great job of showing it, but it looks like it's only touching the point 3, -6. And so I'm convinced that it is the tangent line, even though, I mean, graphically, once we zoom in, it should show it only touching one point, but sometimes it's hard to see in Desmos because, I mean, the resolution isn't crazy good.
Limits of the computer as well.
Yeah, so they're doing estimations on their end too. But great. I like the look of this. I'm convinced that I have done my job. So, phew. Okay, good. Let's see here. Knowing the slope of the tangent line, right? I could also think of this as the instantaneous rate of change, right? At x equals 3, the instantaneous rate of change is -2, so it's decreasing at a rate of 2. So we could also say the instantaneous rate of change. Instantaneous, I lost it. Rate of change at x equals 3 is -2. Good. So nothing really changes from this section to the next, except instead of calling it some specific value x equals a, what we're going to do is we're going to talk about the derivative as its own function, right? Which makes sense, right? We know that a quadratic, right? To touch a quadratic, our line is going to be, we're just going to have a bunch of straight lines as our tangent line. And so they're functions on their own. So we're just going to make that slight extension, but nothing crazy. So before we do that, how about we take just like a 5-minute break, and then we'll do 2.8 and get into it. Let's do just a break until 10:50. Stretch legs. We're back. So 2.8, finally. The derivative as a function. Here we go. It's all built up to this. The derivative as a function. So here, what I just want to clarify is that if it feels like we're doing the same thing, it's because we are. So in the previous section, we found f prime of a, which is the derivative at a point x equals a. The derivative at a point x equals a. So now we want to find f prime of x, which is just letting us put in any value of x. How's that different from what we were just doing? It's not really, right? Letting it vary over x versus letting it vary over y, there's no difference, right? But we like to show it as x, because then we're saying, hey, we can plug in any value of x here and find the derivative. So now we want to find f prime of x at any arbitrary x. So at the top of the notes, we have what we call the limit definition of the derivative. And it's basically kind of what we've built up to, why we need to know all these limit rules, because depending on the function that we have, right, we might need to manipulate the function to be able to evaluate this limit. But ultimately, we're just building up to be able to use the limit definition of the derivative to find the derivative. So here, let's just start by, I'll do a little headline here. The limit definition of the derivative is in our notes here. I think at the very top, and I'll make it nice and big. But also, I'm going to highlight around here because we definitely make you use the limit definition of the derivative. And like I said, later on, we'll have these shortcuts for calculating derivatives, so we don't need the limit definition anymore. So you might be tempted to skip the limit definition when it asks you to use it, but just remember that there will be a question on the next test and on the final exam where you have to use the limit definition of the derivative. In fact, there's one on the quiz as well this week. Oh yeah, did you guys get my my announcement about kind of, so it's got the structure of the quiz, and it'll actually open up right after class. But it does include 2.8, so maybe take some time to review what we're doing today, and then it'll close at midnight on Friday. I'm happy to make that kind of midnight on Sunday or whatever, just let me know, but I wanted it to be out of your hairs before the weekend. So it's kind of a force you to do it before the weekend so you don't have to think about it. But if you need more time, then just let me know. Totally fine. And there's a 45-minute limit. So once you're in there, you have to stay for 45 minutes, or you've got 45 minutes to do it. But yeah, we'll see how it goes. And like I said in the announcement as well, but if you're doing the quiz, or if you know, I'm going to be doing the quiz in an hour, then you can just text me and be like, hey, I'm about to do the quiz at this time. And then I'll kind of know if you text me with questions, because usually my ringer is off. So a little bit of heads up would be good. As I open my phone, I'm like, what the heck? But yeah. So then I feel really bad. But yeah, if you give me a heads up, I can be on call, so to speak. Okay. So one thing that we should kind of be able to do is, looking at a function, we can kind of sketch the derivative. And that's pretty similar to what we did when I said, okay, we found a negative derivative. Does that even make sense? Right? And so kind of having that connection between the original function and the derivative is going to be really useful, mostly for checking our work. So example 1, we're just going to go through, and we're given a function, and then we're going to use it to sketch the graph of the derivative, right? So that we have some idea of what this thing looks like. So I'm going to bring this in, and then I will bring in, oops, of course, the graph, because we need that. And your graph doesn't need to look exactly like this. I mean, if you're sketching it out, it doesn't need to look exactly like this, but this is the one that I'm going to be using. There are some key components that are going to help you sketch the graph of this thing. Okay? So the first one is the fact that at any maximum or minimum value, right? So here we've got 2 minimums. then the slope of the tangent line at a maximum or minimum is going to be 0. So what that maps to, right, if you're thinking about, okay, so now if I'm mapping the derivative is the slope of the tangent line. So here, the first kind of key points that I'm going to map are where the slope of the tangent line is 0. So here, at max or mins, the slope of the tangent line is 0. Right? So it's kind of the first thing that we map out, right? So if we're drawing the derivative, so now instead of having y equals f of x, on the y-axis, we're going to have f prime of x, right? And so here, and maybe I should do this one just a little bit smaller so I can keep it on the same page. Because then I want to have something like this. Okay. And what I want to do is I want to take, okay, I didn't. One, trying to use the same scale, it's hard. 1, 2, something like that. Okay, and I've managed to put it close to a page break, but anyways, so that's going to be your first thing that you're going to pay attention to is when is this thing equal to 0, right? So here, I'll put y equals f prime of x now, if we're sketching the derivative. But then, of course, x stays the same because now we're treating the derivative as its own function, the function of x. So I'll use the same. So if I try to kind of trace this all the way down, and that's why I wanted to line up my axes so that I could just kind of trace them up and down, sort of. We're just sketching, right? And we're not given exact values anyways, so it doesn't really, it's just to get an idea of this thing. And then also here, somewhere like 1.5. And then here, let's say, and it looks like I should scoot that over. Just to make it not look so wonky. Okay. So now the next part that I want to look at is, okay, so the slope of the tangent line, well, I can tell that the slope of the tangent line for all these values up until this 0, they're all negative, right? I'm going down, so I've got a decreasing slope here, right? So it's going down, down, down. And so here, I'll use pink because here I've got a negative slope, then I've got a positive slope, and then I've got a negative slope again, and then I've got a positive slope. So here, I'm just going to do the negative slopes for now, right? Negative slope for both of those pink regions, which means in terms of my derivative, right, my derivative, if it's negative, should be below the x-axis, right? I do have a page break here, so it's going to look a little bit weird, but we're just sketching this thing, right? So what I'm going to do is I'm going to say, okay, well, it seems to be going negative and then reaching 0. And then it's going to be above the x-axis. And then it's going to be below the x-axis again, and it's going to cross the x-axis at this point, right? So what this turns into might look something like, oops, like this, right? So it's negative, negative. And then again, after that second point, it's negative. But notice that it's going from this 0 slope to the next 0 slope. It's negative, but then it's going to cross over. So at some point, it must turn over, right? And so we need to connect these by going maybe something like that. Okay. We don't know exactly what it looks like. That's fine. So now if I do the same thing for these positive slopes, let's use, right? So here now I've got these positive slopes. So it's of course positive where it is a negative. So from here, this point to here, and then this point onward, we've got these, oh yeah, above the x-axis because they're positive slopes, which don't translate to the derivative having positive slopes. It just translates to the derivative being positive, which is what I caught myself kind of reacting to. Okay, there are a couple more things that we could do, right? We could try to translate the slope at the over the y-axis exactly to figure out where it crosses. We don't have enough information. It's not kind of specific enough for us to do that. But in general, this is probably what this derivative would look like. Or in general, right below the x-axis, crossing above, crossing below, crossing above. Right. So, okay, those can be kind of tricky, right? But remembering that at the maximum and minimums, then the derivative is 0. That'll be your starting point, and then figure out the negative and the positive slope, and then just translate those into the graph just. Right. But okay, let me see what's next in here because I had a little note. Okay. So like I was saying before, the derivative doesn't necessarily exist for all values, right? So if we have a discontinuity, for example, then there might not be a derivative. So let's talk about some common situations where there is no derivative. So the derivative may not exist at every point. So some common things that might make f of x not differentiable, and what I will highlight here is that differentiating and taking the derivative or finding the derivative, they're the same thing. So we use those two words synonymously, and so I guess I should do it in a note. Differentiating because I'm about to use it down here. So differentiating and taking the derivative mean the same thing. Which is another one of those things that are hard in the beginning, but as long as you've kind of lumped them in the same group, then we can move on. So some common So some common reasons that a function is not differentiable, right, using our different terminology. So some common reasons a function f of x is not differentiable include first one being that maybe this function doesn't exist at a. So at the value of a that you're interested in, or at some value of a, this function doesn't exist. So the first one is f of a does not exist. So what that means is that a is not in the domain. A is not in the domain. It's pretty hard to find the slope of a tangent line at a point that doesn't exist for the function, right? And so, so that would be the hiccup there. So if you have a situation like this, right? And this is at a, right? So maybe it's something simple like you've just got this hole here, and so a is not in the domain. Then we're not able to find the slope of the tangent line at a because there's nothing to touch. So that seems reasonable enough. Another kind of common situation is if you have a corner or a cusp. So if you have a corner or a cusp, which might look something like, and I'll draw two different situations. One is the absolute value of x. So that's a pretty common function. But if you have something that kind of comes in and then dips down here at a, well, here it's not differentiable at a. The reason being, if you try to, so if you're right at the tip there and you're trying to put a tangent line, well, there's actually lots of different ways that you could angle this tangent line, and it would still only touch one point, right? And so so that's why we can't find the derivative here, because there's actually lots of different options, and thus there's no one solid option. And so we say it's not differentiable. So here we've got this kind of cusp, or for the absolute value of x, we've got, right, same idea. Here at the origin, y equals the absolute value of x. We're not differentiable here. Same idea, slope of the tangent line, it can only touch that one point, and it has to be a straight line. And then, but again, there's nothing to kind of hold it steady. So those are things to keep an eye out for, right? Where is it not differentiable? And then three is if you have a vertical tangent line. So a vertical tangent line might look something like, if you have, I don't know, some sort of, I guess I've been drawing the graph in light blue anyways. Should do it more squished up maybe, because a vertical tangent line probably looks something like that. vertical tangent line, if you think about the slope, so the tangent line has a slope and the slope is the derivative, but the slope is rise over run. If there's no run, right, so straight vertical, then I'm dividing by 0, right? And so then this thing doesn't exist here because I would have to divide by 0, which I can't do. So tangent is undefined since the slope is the rise over run, but run equals 0. So whenever we're dividing by 0, we have to forfeit and say undefined. I am going to make room on this same page here because I just have one little concluding statement. And that is kind of so it's very much linked to continuity, right? And so remember, we were able to say that a function is continuous if we're able to find that the limit at a is equal to the same thing as the function at a, then we said it was continuous. And so there's definitely linkages here, but what we are going to be able to say is that if a function is differentiable, then we can say that it's continuous at that point, right? So if it's differentiable at that point, it is continuous, not necessarily the other way around. So we say if f is differentiable, at x equals a, then f is continuous at x equals a. Then f is continuous at x equals a. So you can add that to the roster of continuity, right? But it doesn't necessarily go the other way. If it's continuous, then it's differentiable. Not necessarily, usually, but can't say. Can't say for certain every time. Trying to think of an example. Can't think of anything, but it only goes one way. So what we're going to do in this section is, okay, well, we've basically talked about the derivative, right? Finding the derivative. We're going to do one example where we find the derivative using the limit definition of the derivative. Great. But then we're also going to introduce some different notations to keep an eye out for. And then we're going to talk about higher derivatives. Can I take the derivative of a derivative? Yes, you can. It's called the second derivative. Can I take the derivative of the second derivative? Yes, you can. It's called the third derivative. Can you take the derivative of the third derivative? Yes, you can. It's the fourth derivative. So you just keep going. What we'll see is that as you take each derivative, the function will kind of, at least in my mind, it'll kind of step down each time. So for example, a quadratic, the derivative of a quadratic becomes a linear function, and the derivative of a linear function becomes a constant. And then after that, there's nowhere to go, right? So depending on how, I'll say advanced your original function is, each derivative that you take is basically going to simplify the function until eventually there's no more derivatives to take. And I remember, going through and finding, the fifth derivative using Maple, and it's actually really fun, right? You save your first derivative. Now there's programs so you can just take the fifth derivative. But back in my day, you had to save the first derivative, then the second derivative, then the third derivative, take the derivative of the derivatives. But so that's what we're doing here. But nothing really changes from what we did before. So let's do this next example here. Copy. We're going to use this function for the other two examples in the handout as well. So just kind of notice that we used in examples 6 and 7 as well. And if you just kind of read ahead, right, example 6, so example 2 that we're about to do, we're going to find the first derivative. And then we're going to talk about, okay, how do the graphs compare? And then find the second derivative, which we just denote with a double prime. And then then we're going to find the third derivative, triple prime. After the triple prime, it gets a little primey. So then we just use whatever the derivative is in brackets, so then we're going to find the fourth derivative. And I've got the sketch here up to the second derivative. So that's just what we're going to do. We're going to find, second derivative, first derivative, second derivative, third derivative, fourth derivative, and then we tap out of x to the 3 minus x. So for A, we want to find f prime of x. Well, f prime of x, so here we're going to use the limit definition of the derivative, which is the only thing we have so far. So then I'm going to find the limit as h goes to 0 of f of x plus h minus f of x. Let me just make sure. Yeah. Over h. Okay. Being careful, because here you've got x plus h and here you've got x, so you have to replace your x's with x plus h, but besides that, no big deal here. So this becomes the limit as h goes to 0 of f of x plus h, which is x plus h to the power of 3 minus x plus h. Put square brackets around that, minus f of x, which is just x to the 3 minus x over h. Nothing crazy going on here, right? But I do need to expand x plus h to the power of 3, and then I'm going to expand all this out, and I'm going to simplify, and hopefully by the end, if I've done everything correctly, this h will somehow cancel out. So let's just do it. So the x plus h to the power of 3, I am going to write it out, and because I suspect that it's going to get pretty large, I'm just going to bump my equal sign over a little bit. I know I should be stacking on mine. Already anticipated it. The limit as h goes to 0 of x plus h times x plus h times x plus h minus x minus h minus x to the 3 plus x. Right, as long as you're careful, I'm just going to expand that stuff and just kind of forget about it. Over h. I like to do one FOIL at a time. So I'll expand the first two, and then I'll expand that into the third. So this becomes, and of course, if you're way faster than me at expanding this thing, then go for it. I am really slow, so that's okay. x squared plus 2xh plus h squared times x plus h minus x plus x. I'm actually just gonna, let's just ditch those right away. So minus h minus x to the 3 for h. I'm going to expand this one more time. So then I get the limit as h goes to 0 of x to the 3 plus x squared h plus 2x squared h plus 2xh squared plus xh squared plus h to the 3 minus h minus x to the 3. Phew. Over h. Out of the woods. So here, I'm just going to try to collect like terms, or at least kind of try to collect like terms. First thing I see is x to the 3 minus x to the 3, so I'm just going to get rid of that right away. Dink, dink. And then I have 1x squared h plus 2x squared h. So this is going to be, I can collect those two. And then I've got xh squared and 2xh squared, so I can collect those two. Okay. So this becomes the limit as h goes to 0 of 3x squared h plus 3xh squared plus h to the 3 minus h over h. Okay. I can pull out a common h just as I expected at this point, right? We've done enough of these to know that, okay, I should probably be able to extract an h. And what I'm going to do is I'm going to cheat a little bit, and instead of showing it being pulled out, sometimes I just cheat a little bit, show it like that instead. So then this becomes the limit as h goes to 0 of 3x squared plus 3x h plus h squared minus 1. Which is the same that I have in my notes, so that is a relief. If I actually evaluate this limit, right, h is going to 0, so this becomes 0 and this becomes 0, 3xh and h squared go to 0. So this becomes 3x squared plus 0 minus 1, which of course just becomes 3x squared minus 1. Therefore, f prime of x, which is what we were trying to find, is 3x squared minus 1. Notice, like I said, right, we started with something x to the power of 3. So now our derivative is going to decrease the power by 1, because now we have x to the power of 2, right? We've got a degree 2 polynomial. So if we have to compare the graphs, we actually have the graphs here. So let's just bring them in. Oops. Oh, I guess this is part B. I should label it. Compare the graphs. And we'll make it small and then zoom in here. So here, right, we started with f, which was x to the 3 minus x, I want to say. Yeah. So here, f was x to the 3 minus x. Knowing a little bit about x to the power of 3, well, I'm expecting it to have this kind of overall shape. Okay, so that's what it looks like. A little bit of activity around the origin, but not bad. And then f, and I should write this as f of x because they're functions. Then f prime of x became 3x squared minus 1, which of course is a quadratic, right? So how do these things compare? Well, right, if we're comparing these things, well, on the function, I'm going to try to identify where I've got a 0 slope, right? And then if I map this down here, that's where I get these x-intercepts from. All right. And then here, right, I've got a positive slope, which means, okay, here the derivative is above the x-axis. And then for this length of time here, I've got a negative slope, which means that for this region here, I'm below the x-axis, right? Negative values between those two x-intercepts. And then same thing here. Now I've got a positive slope again. And so again, here I'm above the x-axis. So same thing that we did earlier, but I know that this can be really tricky. So just kind of take your time. First stop, figure out where your max and mins are, translate those to the x-axis, and then just kind of use that as a guide. Good. Okay. Let's see here. Oh yeah, other notations. So there's quite a bit of description here because I know that the different notations can be really confusing from experience. I know they can be confusing, right? And so there are many ways to denote the derivative. So there are many ways to denote the derivative. So all this is saying is that all of these different notations, they all mean the same thing. They mean take the derivative and set it as a function at x. So we've been using f prime of x. You could just as well have used y prime, and that's because y and f of x are interchangeable, right? Or you could also talk about dy dx, right? So I kind of, so it's the d, I'm pretty sure it comes from delta, so the change. So all these things have, or all these different notations, they kind of come from different places, different fields. And so because this is a general math course, we have to introduce all of them, right? But typically whatever field you go into would use their own, like maybe your field that you choose, I don't know which field it would be, but that would prefer to use this notation. But for this course, as long as you're able to read all of these and say, yep, I just need to find the derivative here, that's it, then you're good. Right. So all of these mean the same thing. So just kind of read through the list and just kind of make sure that you're able to identify that they are all the derivative. So when we use these dy dx, df dx, d dx, for example, these are differential operators. And so I think we've got, oh, and I guess even the capital D. And so here, d dx and d are called differential operators. That part is not important, but because I'm about to use it in the next explanation, I figured I should define it. So using these differential operators actually has one benefit. Although it makes your formula maybe look a little bit harder, it actually has the benefit of hinting at units, especially in things like physics. So physics, chemistry, right? And so we can use these differential operators to kind of figure out what our units might be. For example, and it goes for higher derivatives especially. So using differential operators, I guess this part you can ignore, is called Leibniz notation. Leibniz, sorry. And he is a famous mathematician, but I think he was working in many different fields. I'm pretty sure that's Leibniz. Anyways, there's lots of history out there, but Leibniz notation. And it has the benefit of, I'll say hinting in kind of air quotes, of hinting at the units. For example, especially in, like I said, physics or chemistry. Physics is kind of the easiest one to talk about, right? Because we've already talked about the distance function, the velocity function. We know acceleration goes after that, right? And so, so we already have some idea of the physics aspect. So let's start, let's only talk about physics for now. So if we have x, right, just bare bones x, this is the position which we'll say is meters, right? So where is it? Where are you located? That's your position. That's your x. So now what we're going to say is, okay, if I differentiate with respect to t, and I'm going to attempt to kind of do one of those map zoom in things. D dt means differentiate with respect to t. Okay, so we're going to take the derivative with respect to t. Means differentiate. We haven't done a lot of these, so that doesn't really make sense, but it's okay. You'll see what I mean in a sec here. So means differentiate with respect to t, which really just means take the derivative, right? Or take the derivative, right? So the arrow is just indicating take the derivative of the position function, right? So you have this position and then you take the derivative and then you end up at dx dt. Right? Like I said, we haven't done a ton of this. So of course, if it doesn't make sense, then it's okay. I'm gonna make a little bit more room here. Because then I can just right below dx dt. So if you start at a position function, and we've already done this, and then you take the derivative, where do you end up at? You end up at the velocity. The units for velocity, if time is in seconds, would be meters per second, right? And so here you've got d and d. So here, this is the velocity, which is meters per second. Once we do the next one for acceleration, so if you take the derivative of the velocity, you get the acceleration. So now take the derivative again, and that should be d dt. Where you end up at, right? So here, this becomes the first derivative, and then you take the second derivative essentially, and you end up at d squared x over dt squared. Weird, right? But you kind of, I know it doesn't really make sense, but in my mind, I kind of multiply the d's and then the t's get multiplied, but this is just the notation for the second derivative. And the second derivative is the acceleration. Which is meters per second squared. Notice that here the x is just held as x, and so it's still in just meters, but then t is squared, so it's per second squared. Okay. If you take the derivative again, so take the derivative of the acceleration, this is kind of the lesser known one, but then you end up at d to the 3x over dt to the 3, and this is actually called the jerk, right? And so you've got your distance function, and then you've got your velocity, and then if you take the derivative of the velocity, it puts you at acceleration, and then if you take the derivative of the acceleration, which is just the slope of the tangent line on the acceleration, then you get the jerks, right? So, and then it just kind of, it bottoms out there. So don't worry, there's no more. But this is called the jerk, which in units would have units of meters per second to the power of 3 or cubed. So it's got this kind of, and unless you're doing kind of physics problems, typically physics problems, that would be the case where kind of using these differential operators would be really useful. For us, I'm gonna try to stick to just kind of f prime, f double prime. Sometimes I'll use y prime, y double prime for higher order derivatives. But you do need to see that those are all, they all mean the same thing. Okay. So let's see here. We use f double prime of x to denote the second derivative, which is the derivative of the derivative. And then, of course, just like there was many different ways to denote the first derivative, there are equally many ways of finding or of showing the second derivative. But for now, let's just kind of take a step back and not worry about that so much. So let's talk about how we find these derivatives. And then as the course goes on, we'll introduce some of these differential operators as appropriate. We need to see them, and then now you can forget about them for a while. So don't worry. So as long as you're able to read kind of the f double prime of x, triple prime, quadruple prime, no, then we use bracket 4. Okay, so I know I'm short on time here, but let's do example 6, and then we'll leave the rest, example 7 for next day as a review. How about? So like I said, we're going to use the same function, but now we're going to find the second derivative, and we're also going to interpret the second derivative. So if we have, recall that f prime of x of this thing was 3x squared minus 1 from example 2. Okay. So then if I take the derivative of this now, I can use the limit definition of the derivative again. And so now I can say, okay, well, f prime of double prime of x is the same as f prime prime of x, right? Just the derivative of the first derivative. And we only have the limit definition of the derivative so far, limit as h goes to 0 of f prime of x plus h minus f prime of x over h. That's just replacing f of x with f prime, right? Nothing crazy going on here. Which becomes the limit as h goes to 0 of, I'll do square brackets, 3 times x plus h squared minus 1 minus 3x squared minus 1 over h. Same procedure that we've been doing. Our function, in fact, is a little bit simpler than it was earlier. So this, just to speed ahead a little bit, because I know I'm running low on time. Skipping some work, Martha Stewart style. Oh, and here it is ready. This becomes the limit as h goes to 0 of 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1 over h. Skipping some expansion steps there, but I think you get the idea. I can cancel now. 3x squared minus 3x squared, that's great. Minus 1 plus 1, even better. And nothing else I can do, but I can also cancel an h from each of these. So then this becomes the limit as h goes to 0 of 6x plus 3h. As h goes to 0, this becomes just 6x. Therefore, f double prime of x is a straight line with a y-intercept of 0 and a slope of 6. So, and we've got that graph here. So just like we said earlier, as we take the derivatives, the functions themselves just kind of simplify and simplify, right? So we go from this to the power of 3 graph. And then if we graph it on the same axes, right, we've got this quadratic, and then the derivative of the quadratic becomes this straight line. And you can kind of convince yourself right here is the slope of 0 of the derivative. So that's where it goes through the origin in this case. And then here you've got negative slopes. So it's all negative up until that point. And then you've got positive slopes. And so it changes the positive there. All right. I think that's probably a good place to stop. I'll save some for a review next day. How about?
Sounds good, because my brain is currently doing the power down noise from Star Wars. If you in the first episode, that
especially those notations. It's like, so what happened here? Is there more ways to find the derivative, or no? The rest of the course, we will be developing shortcuts for just how do we find derivatives and avoid the limit definition. So don't worry.
Yeah,
we won't
this
be
is the
using
building block that we are working on chipping down until it's nice and easy to handle.
Yeah. So starting next day, I'll show you some kind of quick tips for finding the derivative. So it'll be really finally get there.
In that case, I'm going to go see about scraping brain cells together, and then maybe, don't know, maybe I'll have a go at the test at some point today. Don't worry about it.
You got time.
I got time.
All right. If you have questions, let me know. Otherwise, I will see you on Wednesday or
Thursday.
Friday.
Gosh, I'm done.
Who knows? I'll see
See
you when I
then.
see it.